Hello guys, today we're going to be talking about radical substitution reactions in today's lecture. Now, we'll be focusing on the reactions themselves, so if you need help with understanding the properties of radicals, I'll post a link in the description from previous lectures or another user. So today we're going to be going over the key steps of a radical substitution reaction, and then the three key components that of the three phases. So you have your initiation, your propagation, and then finally your termination. So in organic chemistry, a radical substitution reaction is a substitution reaction involving free radicals. So as the reactive intermediates. Therefore, the reaction always involves at least two steps and sometimes possibly a third. It uses UV light as well as heat to create the free radicals from one diatomic species. A radical substitution reaction is a reaction which occurs by a free radical mechanism and results in the substitution of one or more of the atom or group present in the substrate by different atom groups. In the first step, called initiation, a free radical is created by homolysis. Homolysis can be brought about by heat or ultraviolet light, but also by radical initiators such as organic peroxides or azo compounds. UV light is used to create two free radicals from one diatomic species. The final step is called termination, in which the radical recombines with another radical species. And the reaction, if the reaction is not terminated, but instead the radical groups go on to further react, the steps where the new radicals are formed and then react is collectively known as propagation, because a new radical is created available for secondary reactions. The initiation step in a radical chain reaction is the step in which a free radical is first produced. A termination step of a radical chain reaction is one in which two radicals react together in the same way so that the chain can no longer propagate. So in initiation, in most cases, this is a hemolysis cleavage event and is most common between halogen-halogen bonds, as we can see right here. And when drawing the arrows, you only draw a half arrow. And so we'll have a halogen turn into two radicals. And then also over here, we draw the same thing with a half arrow, and we get two RO radicals. Another example is down here at the bottom. We have the nitrogen and bromine, and we end up with a radical nitrogen, a radical bromine. And this takes place very rarely due to the high energy barrier involved. Often the influence of heat or UV radiation or a metal conducting catalyst is necessary to overcome the high energy barrier. Molecules such as chlorine and bromine will both undergo hemolytic cleavage to form radicals when subjected to heat or light energy. Other functional groups that also tend to form radicals are right here mentioned below. Next we have propagation, which is a phase that describes the chain of the chain reaction. Once a reactive free radical is generated, it can react with stable molecules to form new free radicals. These new free radicals go on to generate more free radicals, and so on. Propagation steps often involve hydrogen and abstraction or addition of the radical to double bonds. So as we can see in a couple of these examples, I will start drawing the arrows. So the first one, we have our radical right here. And then we have and then this one will go on to there. And then we'll end up with this product with our radical being on the carbon. Furthermore, in this step right here, we have our radical and then coming off the double bond, as mentioned before, and then finally this one going onto the carbon, and we're left with the radical on this carbon. And this goes on until the next phase. Finally, we come to the termination. Chain determination occurs when two free radical species react with each other to form a stable, non-radical adduct. Although this is very Finally, we have Finally, we have termination. Chain determination occurs when two free radicals species react with each other to form a non-radical stable adduct. Although this is very thermodynamically downhill event, it is also very rare due to the low concentration of radical species and the small likelihood of the two radicals colliding with each other. In other words, the Gibbs free energy barrier is very high for this reaction, mostly due to the entropic rather than the anthropic consideration. The active sites of the enzymes, of course, can evolve to overcome the entropic barrier by positioning the two radical intermediates adjacent to one another. So right here we have a few different reactions, and as we can see that these two have radicals, and we'll draw that half arrow, and it'll form a bond between the two, making them both non-radical, more stable structures. In this bottom we have a familiar one, and it'll be the same type, and we'll form Cl2, which is a non-radical stable adduct. Finally, our last portion, we'll talk about how they bond. So, different compounds will have different sizes, and thus the stability of how they'll bond with the molecule. So for instance, with Br, we have a 99% chance they'll form this structure, compared to Cl, when bonded to the structure, has a mixture reaction and can form both of these. Now when looking at the different two compounds, we can see that this one is more stable compared to Cl's second option in the mixture. This is due to the size of the molecule and how reactive it is. For Cl, it is highly reactive and will not wait, compared to Br, which will wait till a lower energy to be able to form this compound. Thank you for watching today's lecture on radical substitution reactions. Hope you enjoyed organic chemistry.